This video is produced by the UCD Math Support Centre in conjunction with the UCD Access Centre. In this video, we will be looking at the Moivre's theorem, and we will also be looking at a proof of this theorem. This proof uses proof by induction. We have a video on this topic if you are unfamiliar with it. The Moivre's theorem is a formula for applying powers to complex numbers in polar form. The theorem states that r times cosine of theta plus I sine of theta, which is a complex number in polar form, all to the power of n, is equal to r to the power of n times cosine of n theta plus I sine of n theta. It's important to note here that on the left hand side, this whole complex number in polar form is to the power of n, and on the right hand side, only the r is to the power of n, and the n goes inside the cosine function and inside the sine function. So let's look at a proof of this. We have a statement of the theorem again at the top of the page. And for induction, our first step is to utilize a base case. So we will let n equal to 1 and show that this is true. So we can see that r times cosine of theta plus I sine of theta, all to the power of 1, is indeed just r to the power of 1, which is r, times cosine of theta plus I sine of theta. Our next step is to let n equal to k and assume that r times cosine of theta plus I sine of theta, all raised to the power of k, equal to r to the power of k times cosine of k theta plus I sine of k theta is true. So we will assume that this is true. Our next step is to show that this is true for n is equal to k plus 1 using the previous step. So we will use the fact that we assume that it is true for n equals k. We will show that it's true for n equals to k plus 1. So we have on the left hand side r times cosine of theta plus I sine of theta, all raised to the power of k plus 1, is equal to r times cosine of theta plus I sine of theta raised to the power of k times r times cosine of theta plus I sine of theta. And this is a property of indices which can be seen in a future video. Now, because this inductive hypothesis for n equal to k is assumed true, we will distribute the k inside using the theorem. R to the k times cosine of k theta plus I sine of k theta times r times cosine of theta plus I sine of theta. If we multiply this out, we get the following line. We multiply the rk by the r, and we end up with r to the power of k plus 1. And inside, we end up with our real parts, which is cosine of k theta, cosine of theta, minus sine of k theta, sine of theta, plus I times the imaginary parts, sine of k theta, cosine of theta, plus cosine of k theta, sine of theta. Now, if we use our trigonometric formula for cosine of a plus b and sine of a plus b, we will get what we are looking for, which is r to the k plus 1 is equal to the real part, which can be simplified using our formula to cosine of k plus 1 times theta, plus the imaginary part, which is simplified again using the trigonometric formula to sine of k plus 1 times theta. So we have shown that r times cosine of theta plus I sine of theta, all to the power of k plus 1, is equal to r to the power of k plus 1 times cosine of k plus 1 theta plus I sine k plus 1 theta.